Okay, perfect. Okay, welcome everybody to another MCRN Colloquium. Today we're lucky to have Dr. Daniel Anderson from George Mason University here to talk to us. He's a professor in the Mathematical Sciences Department. The focus of his research of late has been mathematical modeling and scientific computing techniques, mainly to study problems arising in areas of fluid mechanics, biology, and material science, all relevant to us that are interested in climate. Today, he'll be talking a bit about the stability of floating objects, and I heard there might be iceberg pictures, so I'm excited for that. And with that, Dan, I'll turn it over to you, and thanks very much.
Okay, well, thank you very much for the invitation, Emmanuel, as well, for getting me involved. Um, so, um, yeah, so essentially what I'm going to talk about today is we've been 3D printing things and floating them, inspired by icebergs, but so I'll try to tell you a little bit about what I know about that. Let's see. So most of this work has been done with two different groups of mostly undergraduate students at Mason. We have a experimental geometry lab called MEGL, and started in fall 2021 with a group of 3 students. We had a grad assistant and my faculty colleague. We were both mentors, Evelyn Sanders, some of you may know. And then a second group the next fall, similar makeup, some undergraduates, math students, mostly a couple of mechanical engineering students, and Evelyn and I, and a graduate assistant. So when I first presented this problem to that first group, I said, well, here's kind of what motivates me to think about this. And I showed him this iceberg picture. And so I said, well, what can we say about understanding orientations of static and maybe dynamic floating objects? And in particular, maybe understanding observed patterns on the icebergs. And I added here floating related patterns because I'm not sure I want to attempt to describe the details of this kind of irregular structure where this thing is presumably broken off from some glacier. But I'm thinking of things like this line here that looks like a water line from some previous orientation of this iceberg. We're motivated by the shape evolution problem, deformation, so like melting or calving events, and then possible tipping and rolling events as well. Here's another picture of some what I think are most certainly grounded icebergs, but there's this one in the back here is kind of has a clear history of some changes in orientation with respect to the water line for one reason or another. So I found icebergs like that kind of fascinating. Here's another one that was definitely a grounded iceberg. I think it was described as being around for maybe several seasons. And there's some interesting wave-influenced erosion near this water line. There's possibly some things going on with the tide. So a grounded iceberg will have the water line will go up and down. Obviously, I think I probably took this picture because I like this kind of broken structure, but then realized there's something interesting happening down here as well. This iceberg is a freely floating one, and I'll try to describe it. It's a still picture of a video. It's not the greatest image here, but I'll try to describe what you see here. So it's a pretty big iceberg. There's a ship in the background here, a little kayaker over here on the left. And there's a little bit of the iceberg kind of hidden in the back, kind of behind where you can see. But this thing is sort of slowly rolling in the water, pretty gently on the one hand. It's it's sort of satisfying Archimedes principle. It's not going up or down very much, but it's clearly rolling. And the image I want to sort of convey is some sort of, this is in some sort of potential energy well that's kind of characterized by some rotation angle. All right, so with that in mind, so what I'll try to describe today, maybe not quite as bold as some of those objectives, but I'll try to talk about static floating objects, freely floating, but not grounded. And we'll think about uh, a, a simplification where the object is long in one direction, but a uniform cross section. So basically two-dimensional mathematical objects, but otherwise pretty general cross section. And so we'll take a look at some modeling, computation, and some experiments with some 3D printed objects. Now, one of the first things one thinks about with floating things is Archimedes' principle, which says the upward buoyant force exerted on an object wholly or partially submerged is equal to the weight of the displaced fluid. So if you have a freely floating object not subject to any other forces, you'd have this balance between the weight of the object and then this buoyant force. And if you kind of disassemble that a little bit, you can write that as the volume ratio. So submerged volume to the total object volume is equal to the density ratio of the object. This could be like an effective object density divided by the fluid density. So if you know this number, then you can predict how these things are going to float in terms of their volume ratio. Now for sea ice or for just pure ice and water, that ratio is pretty close to 0.9, a little more, a little less, depending on details. And I think that's a pretty sort of familiar notion of this, 90% of the iceberg is below the waterline. So if you have something like a tabular iceberg, so maybe something that looks like one of these, at least from above, and you have a freeboard, so the height above the waterline, that's maybe 10% of the whole iceberg depth. When I started looking at these other pictures, I'm like, well, I'm not sure all those are exactly that shape. And so I thought, well, if you think about a spherical iceberg, that ratio, this freeboard to draft, freeboard to the sort of the whole depth, or that's about half of that. So it's F is about a fifth of this diameter. And here's an iceberg I made in my kitchen on Saturday. So just to convince myself that that's about what it does. Okay. So obviously there's been a lot of thinking about how things float from the point of view of things like ships and other boats. This is just an extremely brief review of that. So but there's certainly a couple papers to start digging. Icebergs, obviously, we're interested in. Some of the things I'll talk about today are more directly linked to some of these other cases of long objects with uniform cross-section and uniform density. So I'll talk a little bit about the square. So that's kind of a pretty simple shape, but it still has quite a lot of interesting structure to it. People have looked at things like rectangular cross-section, triangles, etc. One of the things our students found right away was this thing called the iceberger or iceberger remixed. and it's a couple of different web links, and you can go in there and draw your own iceberg. So here's the Colloquium logo floating as an iceberg. So that's fun to kind of play with and get some intuition about how things float. I mentioned the square, so people have looked at that since maybe the earliest 1963. We've done some work on that. I'll describe a little bit more later. This group, Feigl and Fusilev, in 2021 had a nice set of calculations and experiments that showed kind of what can happen with just a simple shape of a square. So this graph shows, so on the horizontal, it's the density ratio, so from 0 to 1. The notation I'll use is a little bit different, so don't worry about the notation, but it's basically the object density to the fluid density, and that goes from 0 to 1. And then on the vertical is some representation of the orientation of the object. So this goes for the square, because of the symmetry of the square, it goes from 0 to 45. So what you see for the square, so at this kind of low end of density, so near 0 or up to maybe 0.23, something like that. This angle is 0. The object floats kind of flat side up pretty high in the water, maybe not too surprisingly. In the middle region here, say around density ratio 0.5, so the object is about volumetrically about half in and half out of the water. The square floats corner side up, or corner up. And then over here for high density ratio, so iceberg would be something like 0.9 over here on this right side. So then you have a square floating flat side up again, sort of deeper in the water. But for the square, there's these transition regions also near density ratio 1/4 and 3/4, where you get that whole range of orientations from 0 to 45. So as you sort of cover this little window, it's a little bit less than 0.25 and a little bit greater than 0.25. You get these sort of off or tilted shapes, and then there's a similar one over here for 0.75. Okay, so that seems kind of interesting, even though the square is quite a simple shape to think about. Then there's what's called Ulam shapes. So these are two-dimensional cross-sectional shapes with no preferred floating orientation. So if you think of like a potential energy landscape, and I'll show you some of these in a little bit. So it would be perfectly flat. So there's no preferred floating orientation. And so the simplest one of those would be a circular cross-section. Right, so you could kind of imagine a cylinder floating. There's no particular preferred orientation. And this is sort of the main feature of these lumberjack and log rolling competitions, where try to stay on these as long as possible. And apparently it's not hard enough to stand on one by yourself. You have to get on there with somebody else and then see who wins, who can stay on the longest. So this is an example of that. Perhaps more curiously, there are other cross-sectional shapes that aren't circles that also have this feature of no preferred floating orientation. And this is one of them that was illustrated in a paper by Gilbert in 1991. I think this one has density ratio 0.5, so it's sort of half in, half out, but there's this kind of curious notion that there's kind of a non-trivial shape, but there's still no preferred orientation for floating of that object. Now, if you go back to circular cross section. So from the point of view of like just a floating log, there's no particular excitement in terms of like what's the orientation of the floating rod, unless you're standing on it, of course. But the story changes if you start melting this cylinder. And this is some work that a group up at NYU, Riestroff and co-workers had a poster at the APS Division of Fluid Dynamics meeting last November. And so what they did, they took one of these cylindrical shaped piece of ice at time 0, put it in water. So it's sort of room temperature water. And then just watched what happened. So what happens is that this thing starts to melt on the submerged surface. And then as that occurs, this cylinder becomes top heavy and it kind of flips its orientation at some point, reaches a new stable orientation, but then it keeps melting and then it keeps getting top heavy and it flips again. So this is a picture of that sequence over a few different flips. And what you see is that this nice cylindrical shape evolves to something that's pretty irregular. Eventually disappears in this experiment, but there's some interesting dynamics along the way. And of course, there's some interesting fluid mechanics of the melt fluid coming off this melting object. Okay. Right, so let's get back to maybe some of the mathematics. So I mentioned Archimedes' principle. So we have this volume ratio that's dictated by the density ratio of these objects. Two other quantities of interest here are the center of gravity of the object, call that G, and the center of buoyancy, which is the centroid of the displaced fluid region. So that's called B in this notation. Hopefully the notation is clear here, but I'm generally thinking of the object mass as the density of the mass times the volume, with those being constants. And then, the submerged mass is referring to the the displaced fluid. Maybe that would be a better subscript for that. But but anyway, let me know if there's any questions about notation on any of this. So Gilbert, this paper I mentioned once already, showed that you could identify a potential energy function that was basically a function of orientation. I'm thinking here of a two-dimensional object by thinking about kind of two pieces of that contribution. So work done by gravity, work done against gravity to displace an object relative to some reference point. And so you can write that in terms of the center of gravity of the object. And so you get changes depending on whether you move against or with gravity. And then there's another contribution from the kind of the buoyancy related part, and that's the work required to bring the displaced fluid particles up to the level of the air-water interface. And then if you impose Archimedes' principle, so assuming that this balance, which is essentially a vertical force balance on this floating object, applies, then you can write down a potential energy function that involves the center of gravity, the center of buoyancy, and then this normal vector is really the normal to the fluid interface. So I imagine that pointing out of the water, say. So with Archimedes' principle and then this potential energy function, that's essentially enough to kind of describe a a stable floating configuration. So essentially what we did, we said, well, okay, we can do that for any, we'll specify any cross-sectional shape. And we're thinking of polygons. So it could be the square, or it could be something really a lot more complicated than that. We'll compute the center of gravity. And then for each orientation of that object, we'll adjust it up and down to make that floating shape consistent with Archimedes' principle. And then for that configuration, we'll identify a center of buoyancy as just the centroid of the displaced fluid region, and then build up this potential energy function with those things, and then just look for the minima of those of that potential energy function. Now, in practice, what we'll do is we'll fix the shape, and then we'll rotate the water line. It's just a little easier to do computationally. So I may describe it as if we're doing that, but it's really in the lab you might throw a object in the fluid and then just kind of help it move around, sampling 360 degrees worth of orientations. So people have done this for simple shapes, squares, rectangles, and we said, well, we can do this for any shape, and if we make use of Evelyn's 3D print skills, we can also print them and see if we can float those as well. And so our basic idea was to say, well, let's design some shapes in that we can make. We can 3D print. We'll have a control on this infill percentage. So if you've used 3D printers, you know what that is. But if not, it's essentially a control that you can specify as you set up the print. And it's the way we essentially control the effective density of the object. So in this picture below here with this thing we call a triangle, this is one of our sort of bigger shapes we floated. But if you look closely, hopefully that's clear enough. That's about 80% infill on that. This happened to be a failed print that didn't print all the way through. So generally our prints that we would float, you wouldn't be able to see the inside because it's so it's in principle watertight. But for infills between, say, I don't know, I think the lowest we usually go is like 5% and up to about 90% maybe. So that covers a range of densities from 0.2 up to 1, and anything above 1 is going to sink in water. So it gives us a good range to kind of play around with. We started out mostly with squares. I'll show you a little bit of a few results for squares with offset holes, so we can kind of move the center of gravity around in a controlled way. But here's kind of the basic description of what we do. So it's we've put together this thing called the Iceberg project. It's in a GitHub link, and all of this stuff is available there. It's maybe medium user-friendly, I hope. But anyway, the idea is you pick your shape, maybe you have an image or you just draw something, and there's a little routine that Evelyn and one of her grad students wrote up that picks out the boundary that gets fed into the 3D print software, and if you use the extrude command, you can print any of these sort of shapes, send that to the printer. Here's 3 shapes: a duck, this one we call the monster, and this one is butterfly. So you have these physical objects now. You can run those shapes through the MATLAB code that we have that computes the potential energy as a function of angle. This particular case is for this middle print. And I think So one of the things we do, so we get the print, we measure its mass, and then compute its effective density. So yeah, so this one is maybe like 0.4 density ratio, something like that. Anyway, so the prediction is these two orientations as stable orientations, and then here are those two observations of this 3D printed object floating in water. Okay, so that's kind of what we do. You can be as sort of creative as you want on this level. Evelyn runs a capstone course where this is one of the projects. So the students design their own shapes and run it through this software, print them, and do a little experiment in class. So it's kind of a nice little thing you can do. So I'll go back to the square. So I won't talk about this one again, just to remind you that there's these kind of this range of orientations for the square. But we did this sort of 3D print process with the square just to make sure that we could repeat that case. In the middle plot here is orientation angle as a function of density ratio. So again, if we're up here, density ratio 0.9, so that would be something like this floating shape here. There are the square has 4 solutions, right? One for each sort of this rotation of the square. So that's the prediction. Here's an observation from the lab of one of the floats. And then the potential energy function has 4 minima, and that's what these solid lines are. The 4 points here at around 0.9 are actual observations of floating objects. Similarly, in this middle range of density ratio, so these objects float corner up. So here's an example of a red square. It happens to have a nail in the middle, floating corner up. And then these kind of in-between cases, so there's actually 8 of them. If you can confirm that there's, we didn't assume symmetry. Sometimes we didn't want to assume that these things we printed were symmetric, mostly because of the infill, and I'll say that a little bit about that in a minute. But anyway, we're able to find the 8 solutions here, and the potential energy looks something like this. So there's 8 minima in this one. This is a density ratio of around 0.23, so kind of in this transition range. Especially for the low 3D print infill cases, it's easy to get for the square, the symmetry to break. And so we decided we would do that maybe in a more controllable way and put these holes in and fill it with a nail. And so we just did a couple of calculations in that example. So with the so this nail is sort of moving towards one of these corners. So when that's up or down, then it floats pretty symmetrically. But when it's off to the side, you can see it kind of tipping one way or the other. So there's a little symmetry breaking there. If you do a quick look at the theta versus density ratio plots, so you can just go back. So this is the perfectly symmetric case, and then as you start breaking that symmetry, you see these solutions going away. And the further you move this nail out to the corner, it obviously prefers that corner be floating down. So that's this solution that you see kind of through most of the range of density ratios. We managed to get reasonable comparison, but maybe not perfect. So these 4 data points are the observations from this previous floating object, and we found those matching up here for the center of gravity. That was actually what we actually think it was. Those points have those kind of isolated solutions have actually disappeared. So we're pretty close on that one, but maybe not perfect. So the excitement for us for the 3D print thing was we could make any shape, so we don't have to just do squares. And so we played around with this thing called the Mason M, which was our previously our favorite university logo. This one, I'll call it the version without the feathers, but this has four stable floating orientations, and that matches up pretty well with what we observe in this potential energy landscape. So these red vertical lines are our observations of these four orientations, and they line up pretty well with the minima you see in the potential energy. So I'll give you a little bit of a quiz right now, just so you're see if you have a chance to make a prediction. So this is the Mason M with feathers. Okay, so the Mason M has two extra feathers. It's supposed to be a quill, if you look at it right. And it looks like they're disconnected, but mathematically we've connected them with a line of zero mass. So it floats as if they're in that in the configuration you see. So in this grid of four by four plot, so the density ratio for this M is about 0.9, I think. There are two stable orientations, two stable equilibrium orientations, and two unstable equilibrium orientations, and the rest are just not in equilibrium. So I'll give you a minute to see if you can pick out, maybe just try to pick out the equilibrium, the stable equilibrium solutions. And while you're doing that, I'll give you a little sad story. So since we've been playing around with the Mason M, the university has changed its logo. So we now have this as the university logo. And one of Evelyn's students floated this in their course this semester, and I haven't seen it floating, but I've been told that the results are slightly disappointing compared to the original Mason M. So they didn't consult us on this logo change. Anyway, so does anybody want to venture a guess as to the two stable orientations? Probably a small enough group, somebody can just shout out if they want.
Is row 1, column 2
Okay.
stable?
That's one of them, correct? Do you see another one?
Row 4, row 3, column 4, perhaps.
Yep, that's the other stable one. Very, very good. A fairly common guess for stability was also column 3, row 2. So this one, and then also row 4, column 3. But those are actually unstable equilibrium solutions. So I'll show you the potential energy plot. So this one is sitting in this well, this one is sitting in this well, and then these sort of ones that are kind of perfectly up and down, or those are exactly where it kind of flips from one way to the other. So well done on the quiz. Okay, so in the spirit of icebergs, so we wanted to float the Mason M and say, well, what happens if you like lose a part of this iceberg? And so here's the M floating in a stable orientation. And then if we remove this upper feather, what we see that we've got a slight orientation change. And I've drawn in where the water line used to be. So we're not doing anything like melting of this, but in principle, one might see some sort of signature of this water line in this newly oriented thing. So I felt like, okay, maybe there's a chance that something like that could happen for a real iceberg. Okay, have a little bit more time, I think. So I want to very briefly just show you one other thing we did. So kind of lose the connection to icebergs here, but one of the things we were curious about and are no longer curious about, because I think we understand what's happening here. So what happens for shapes if you float them at a two fluid interface? So for example, some experiments we did were say water and oil interface, or corn syrup we played with, or oil and corn syrup. Same setup in terms of the geometry of the objects. We tried a few different shapes in this case. Archimedes principle works pretty much the same way with you just have to keep track of masses of regions of sort of two fluid regions. So this is a fluid one, density rho 1, density rho 2. So this object is floating at an interface like that. Archimedes principle, just again, it's essentially the same statement, and you just have to be careful how you write that with the mass of the object, or the weight of the object, and the weight of the displaced fluid, just keeping track of the two different fluid regions. But you can kind of manipulate that and get that into a condition on the submerged area 2 in terms of an apparent relative density. So you adjust it with this upper fluid density, and then kind of have the same story. We weren't sure if that would work for the potential energy argument, but it turns out, and I won't talk about too many details here, but the previous potential energy involved the difference between the center of gravity and the center of buoyancy of the object. And then for this object, the center of buoyancy in principle needs to be calculated with knowing sort of both of these fluid regions. But if you work out the details, it turns out you can write this potential energy just in terms of the centroid of the object the fluid 2 object. So we realized the only thing we have to do differently in our code to solve the two fluid problem is just change the density ratio from the object density over rho 2 to this relative one. But otherwise, everything works the same. The experiments are 10 times messier, so we didn't have quite as much fun doing the experiments, but we were able to get some results. Let me just skip to one example. So this is a shape we call the arrow, and this is floating at a oil-water interface. So we floated a bunch of different shapes in a bunch of different systems. Here's some predictions for a particular density ratio and some observations that we felt were pretty reasonable. If you look for differences, you'll start seeing a little bit of things that are different between the predicted version and the actual version. But anyway, we felt like we were doing a pretty good job in some cases. One of the challenges for these small objects we think is surface tension, and not really a big deal for sort of climate and iceberg dynamics, but certainly for these small objects. And so we knew that right away so we looked at this plot. So this is R observed, so we could take a look at what's the submerged area just based on what we see experimentally and what we expect to be the case based on these density ratios of the fluids and the object involved. And in some cases, so ideally they fall along this diagonal line. In some cases, especially the higher density ratios, they're pretty good, but in other cases they're pretty bad. And we think there's some sort of complications. These tend to be the oil water systems, so we think there's some surface tension issues and some issues with entrainment as well. Anyway, we did a lot of experiments and made some comparisons. This is just a particular example. If you look at the middle plot, the orientation angle versus density ratio. So again, maybe for an example, on the low end of density ratio, there's 3 solutions. So there's one at angle 0 and then 2 symmetrically. And that would be this situation. So this arrow kind of standing up is angle 0. And then if it tips one way or the other to these states, that's what we see for kind of small density ratio. For large density ratio, it's kind of an upside down version of that. So it's like a V floating V shaped. So we can do a pretty good job of comparing observations with predictions there. So let me do a quick summary and then have time for questions if there are any. So we've developed computational tools for and 3D print designs to explore the stability of long floating objects with 2-dimensional uniform cross-section, but otherwise very general shapes work in this code. And if you can print it, then you can at least try to float it in this scheme. We've looked at both single and 2 fluid situations. And there's a code here if you're interested in anything that floats, predicting it or sort of figuring out how to design and 3D print something like this. Some of the current FU efforts we're thinking about, at least, kind of curious about putting in a grounding effect. So there's some feature of this floating iceberg that's partially supported by something underneath. Shape evolution is certainly something we're interested in. And then, as I mentioned, there's several non-iceberg related things like surface tension, and also there's a question of, like, in these water syrup situations, there's a possibility of kind of mixing and continuous density stratification. So I think that's my summary. I think our Mega Lab and the Maker Lab again put up some references here. If you're interested, I can direct you to any of those. But thank you for your attention, and happy to answer any questions if you have them.
Okay, great. Thank you very much, Daniel, for the really interesting talk. So first, I guess let's thank our speaker, and then we can open it up to questions. If anybody has any, feel free to chime in.
I have a question.
Yeah.
Unless somebody else has one, I'll let them go first.
I have a question.
Okay, go ahead.
So I was wondering, when you're calculating those kind of theoretical curves for like what you expect in terms of orientation to density ratio, how could you remind me how you calculated those curves?
Oh,
again?
right. Yeah, I'll go back to the square. Yeah, so for this density ratio, say 0.23 for the square. So what we do is, so we say, okay, let's figure out where that floats up or down to satisfy Archimedes principle, and then run the use my right hand here, run the compute the potential energy for each orientation. So run that through 360 degrees. And then that gives us a potential energy landscape for that particular density ratio. So in this case, there are 8 local equilibrium, local minima. And so for that, in this central plot here, so we go to 0.23 and then just plot those 8 orientations in this direction. So that's how those are defined.
Okay, so you're running it through like a grid of points as opposed to like a function.
Yeah, so we literally, for each density ratio, we'll compute that whole potential energy function. And then like to generate this plot in the center, we would do that for a range of density ratios. Yeah, so it's doing a lot of computations, certainly for the square and maybe some other cases. There's more direct ways to do that. But yeah, that's what these theta versus R plots are, basically just showing where the minima and the potential energies are. And so you see these kind of transitions as a function of R. Yeah, good question.
There is a question in the chat.
Let's see. Can I figure out how to do that?
From Adrian Castaneda.
We can read that for you if you'd like.
Yeah,
Adrian.
I'm not sure. I'm not seeing my link to open the chat.
Okay. Adrian asks, does your density change depending on the material you're printing, like plastic, I'm assuming PLA, P-TEG, or carbon fiber?
Yes. Let's see. Maybe I'll go here. Yeah, so we've typically used PLA, which, if I remember off the top of my head, is more dense than water. So a solid chunk of PLA would sink. I want to say 1.2 or 1.3 compared to 1 grams per cubic centimeter. But yeah, so that certainly controls the density of the object. We have a way to kind of roughly guess what the density of the object will be before we print it, but we don't have a good scheme. So basically, essentially what we do is after we print it, knowing its volume, we weigh it and then assign an effective density. But yeah, different materials in the printer would behave a little bit differently. Our primary material has been PLA, but I think even one roll of PLA to the next roll of PLA is not necessarily uniform.
Okay, so my question, unless anybody else has other questions. I mean, first of all, shout outs to
Hans, do you have a question? It looks like you're muted still.
you're muted, Hans. You're muted.
Yes, so here I am, unmuted. But you go ahead, Emmanuel.
Oh, okay. I mean, yeah. So then in your steps, right? So first of all, I mean, when you showcase this, you said you identify the water line, right? Then you compute the center of buoyancy, and then you compute the potential energy, right?
Yeah.
And the idea is to minimize this potential energy. So in your minimization, right? Do you do so to find the stable, unstable configuration of this object, or is there something in particular that you're looking for when you're minimizing this potential? Of course, you're looking at the bottom of this well, but what?
Yeah. Yeah. So since we literally compute the entire function U of theta over the whole range, then we just numerically identify a minimum value. So I think a preliminary version of our code, we just sort of, find in this vector of values of potential energy, we just find local minima. We've since done a little bit more terms of some fitting of that potential energy. But other than that, we don't have any direct way that we're computing a minimum. So we have the function numerically, and we just sort of directly identify where the local mins are. And it's just of one variable, this rotation angle.
Okay. Then one last question. So then you're looking at the work done against gravity to displace an object, and you're looking at the work required to bring the displaced fluid particle, right? And you also looking at the center of gravity, taking into account the center of gravity. So then in your general formula, is there an overall thing that adds all those work values together, or is just each part separately?
Yeah, so these two contributions to the potential energy get added together to generate this thing we've called U. So there's a reference shift here that doesn't matter in terms of identifying the minima. So that D is just a fixed reference point. So this really ends up being the things you need to compute that potential energy are the center of gravity of the object, which you could pre-compute because you know the shape. And then the center of buoyancy depends on where it's floating. So in our actual computations, we fix the object and then just let the water line rotate 360 degrees. So it's a little bit counterintuitive from the point of view of something floating in water, but it's easier computationally just to move that line.
Thank you.
I'd say go ahead, Hans, if you.
Okay, I'll ask my question. So I was sort of intrigued by your comment that you were interested in grounded icebergs. So what new do you expect to find? In my thinking, a grounded iceberg is sort of fixed. But what are the variables that allow you to study partial grounding or whatever?
Yeah, so I mean, I guess let me go to the square for example.
Yes.
So if I look at this particular square on the right, so it's floating flat side down. So if that's not able to float all the way in that configuration, say it's not deep enough, but the ground, I want to say, using the wrong term, is flat, then it's just going to float a little bit higher. But if it's a sloped surface, then this is going to change the angle at which this thing wants to float. So I'm thinking of sort of a partially supported iceberg. Yeah, and for example, something in this configuration. Now, I mean, an iceberg is not going to have a density ratio 0.5, but it may also not be square. So it may have it just may not be allowable to float in its sort of preferred free orientation. But maybe as sort of tides go up and down, these things could sort of somehow adjust. That's what I'm wondering about. I mean, maybe a lot of people know more than I do about this. But I'm just thinking like something like this. So is just like the tide goes up and down and it kind of rocks back and forth on some subsurface. Or is that something else? Anyway, that's what I'm kind of curious about. Not sure I've formulated any grand plan there.
I didn't expect a grand plan. But for example, I was thinking about calving of icebergs, which happens sort of, these icebergs are held up because there are ridges underneath. Is there any way that you could incorporate those things in your model? Because icebergs, when they finally reach the ocean, the outer shelf, then they tumble down, as it were. But
Yeah.
unless they're held up by these ridges play a very important role on the melting of ice caps.
Yeah.
Is that anywhere in your model?
Not in this.
Not
Not in this.
no, not in the moment, but in your
Yeah.
plans, let me say.
Yeah, I mean, I think I'd be interested in just, putting some simple um, structures below, but flat or sloped, or maybe if there's some interesting features like ridges that could be sort of factored in somehow. Um, um, it seemed like there would be a way to do that with this, maybe at least in sort of a 2D context. So you have sort of a constraint on Archimedes principle. You can't satisfy it because it doesn't float low enough in the water. So you does the best it can with the constraints that the object has to be above some baseline. I'm forgetting the word for like what what is that called?
You mean the ridge?
Yeah, isn't there a sort of a geological term for
I'm sure there is.
the bottom of the ocean? Anyway.
Okay. Well, thank you.
Okay.
So, okay, if I may ask one more question.
Sure.
Is it possible to simulate or to design an experiment where you have a tumbling iceberg that keeps turning on a time scale of God knows how many years? But that would be an interesting project. I mean, how does that?
Yeah.
How does the geometry influence the motion of the iceberg as it melts underneath or on the side or whatever?
Yeah. Yeah. Well, I think these guys have a
Something like that.
paper coming out pretty soon, or I know they're working on it. So I think there's probably something coming out in that direction, at least in the context of describing what these observations are here. But yeah, that problem is very interesting to me. I would be interested in. That's kind of why we started floating things in the first place, to kind of understand problems like that.
Okay, well,
Any other questions?
looking forward to your next experiment.
Excellent. Okay. Well, I will, if you guys have one more minute, I will show you a video, but maybe I'll have the organizers turn off the
recording for sure.
turn
Yeah.
off the
For possible copyright reasons, I think, right?
yeah. So let's see.
So I guess with that first, well, I just want to say thanks again, Dan.
Oh yeah, thank you.
Wonderful talk and great discussion, everyone. And we'll see you again next week, as usual.